talk. The work we're going to be talking about is the ability of rain to transport thermal energy within permafrost landscapes. So this is a landscape that I'm sure many of you are familiar with. We have a black spruce permafrost forest, and then in these lower lighter green areas, we have areas where permafrost is thawed. This is ice-rich permafrost, so the ground subsides, and then we get the formation of a wetland. This is a simplified cartoon representation of that landscape, and when we're thinking about the the climate consequences of such a landscape change, so the conversion of a forest into a wetland, we know that immediately with permafrost thaw, we can get a loss of carbon that had been stored in the permafrost. But it turns out that wetlands are actually highly productive, and so over longer time scales, so say centuries to millennium, these wetlands can actually pull more carbon out of the atmosphere than was lost with this permafrost burst. And so we can actually have a net cooling impact on the climate on very, very long time scales. However, in kind of more near-term time scales, so say, decades to centuries, we need to account for the fact that wetlands often are producing and emitting methane. And we all know methane is a potent greenhouse gas. And so I would argue that on the time scales that we're thinking about in terms of setting climate policies and running climate models, methane is really often the control on what the radiative climate forcing is associated with this type of landscape transition. So a quick primer on methane. In these anaerobic wetland soils, organic carbon can get converted into methane through a whole consortium of different microbial communities. Excuse me, sorry. So when we're thinking about factors that influence methane production, plants are a really big player, and that is because carbon fixed by plants, some of it gets allocated below ground to the root system, and some of that carbon can ooze out into the surrounding soil, and that can actually fuel and support methane production. Many of these wetland plants also have hollow tissues inside of them called parenchyma. These tissues are there to get oxygen from the atmosphere down to the roots of the plants, but these tissues also allow methane to escape from the soil up into the atmosphere. So plants are a really big player within the methane cycle, and often methane emissions are tightly correlated with plant productivity. Temperature is also a really important variable, in large part because microbial rates speed up with temperature. So that means that we're going to have more methane getting produced in warmer soils. However, we can also have microbes that are converting organic nitrogen into plant available forms of nitrogen. And as that process speeds up, we can increase nutrient availability to the plants. And so we can also, with temperature, see an increase in plant growth. And then, of course, that can feed through and have an impact on methane emissions. So I've been working at a field site outside of Fairbanks. There's here a thermokarst thaw bog. And we actually began working at this site to focus more on plants and the role that plants play within the methane cycle. But it turned out that in the 3 years that we were working at this site and doing other studies, we captured 2 of the rainiest years on record. So 2015 was an average precipitation year, and then the year preceding that, 2014, and the year following that in 2016 were 2 of the most rainy years on record. We ended up seeing in one of these rainy years, 2016, that site level methane emissions increased by about 30%. And an obvious question is why? So why are we seeing such a burst or such an increase in methane emissions just in this one rainy year? And the spoiler alert is that it has to do with the title of our talk, that it's related to thermal transport by rain into the bog soils. But what I want to do first is kind of step you through the smaller pieces that get us to that bigger answer. So the first answer to this question, why, has to do with plant productivity. So what we found is that Carex aquatilis, the primary species, that's the sedge plant that I'm showing here in this cartoon. It is responsible for much of the methane emissions at the site. And so what we saw is in 2016, this one rainy year, we had almost a 200% increase in coverage of Carex aquatilis just at the edge of the bog. In the center of the bog, we didn't see much of a response. And then obviously in the other years, even at the edge of the bog, not seeing too much of a response. Correspondingly, and when we had this big increase in Carex coverage, we had a large increase in the amount of methane being emitted at the edge of the bog. And similarly, not much of a response in the center or in these other years. So part of the answer to why this big increase in methane emissions had to do with this increase in plant productivity. But that, of course, so this is summarizing what I just said. But that, of course, leads to another why question. So why this increase in plant productivity just at the edge of the bog just in 2016? The answer to that question has to do with soil temperature. So the data I'm showing here are the penetration of 10 degrees Celsius temperature into the bog soils. This is for the center of the bog, and the lower plot here is for the edge of the bog. And then the colors correspond to the 3 years according to this legend down here at the bottom. And so what we see is that soils at the edge of the bog warmed up about 20 days earlier than the soils did in other years within the edge or even in the center of the bog, so in other locations. And so it was really this early warming of the bog soils at the edge, which we think increased the ability of microbes to start generating plant available nutrients. And it's really the beginning of the season when the plants are taking up all of these nutrients out of the soil, and it helped then this Carex to grow and plant productivity to increase and methane emissions to increase. But of course, this leads to more why questions. So why just the edge soils? Why were those the only ones experiencing warming? The answer to that is connected to our rain events and the fact that we're seeing rain delivering thermal energy into the bog. So what we saw is at the bog edge, we were getting rapid changes in soil temperatures down to deep depths that were corresponding with rain events. So this color plot here is soil temperature based on the color bar as a function of depth and then over time. And then the top panel here, these squares show rain events and the approximate temperature of that rain when it fell. So to a first approximation, rain has the same temperature as air. And then these black arrows are just denoting kind of key rain events. These are rain events where more rain fell, and the gray bar is showing the duration of those rain events. And so what we can see is here we had a particularly large rain event, and you can see this rapid warming of the soils down to almost 80 centimeters depth. So we're seeing rain delivering thermal energy to the bog soils when that rain has a warmer temperature than the soils do. We can see that warming. Okay, so another why question though is why just the bog edge? Clearly when it's raining over the whole landscape. If you look at the depth to which this rain fingerprint is penetrating down into the bog, it's much too deep to account for rain falling directly on the bog itself. So we're not getting, 80 centimeters of rain in a single rain event. What's happening instead is that this rain is falling across the landscape and traveling from these permafrost plateaus down gradient and then plunging and entering into the bog at the edge of the bog, and then traveling through to the center of the bog down at these deeper depths. And this kind of flow pattern is supported by our temperature data. So here's this big rain event in 2014. I'm plotting here temperature as a function of time, and each of these lines is a temperature sensor, the depth according to the colors. And so you can see that we have this big rain event, and then about 5 days later, we see a complete collapsing of the temperatures. This is at the edge of the bog in the shallow soil depths. So supporting this idea of the water just kind of plunging in after it's kind of flowed through the rest of the watershed. And then you'll notice in the center, it's quite interesting, the top temperatures are not warming up, right? It's just the deeper soil temperatures which are experiencing warming. So this idea that the water is coming in, plunging down, and then traveling at depth over into the center of the bog and warming just the deep soils and not the shallow soils. So it's not rain falling directly on the bog, it's this connection of the bog with the rest of the forested watershed. And so the key is in 2016, rain fell in the spring. So 2014, 2016, similar amounts of rain, but the timing was quite different. And so the reason why we were seeing such a response in 2016 is because really we had rain falling early in the season, and it's this early warming of the soils which facilitated all of the biogeochemistry. So I just want to kind of step you through everything that I just brought you through, but now we're kind of working backwards from the way that I presented it. So in 2016, we had spring rainfall. That rain fell across the landscape, and water from the permafrost forest flowed downhill into the bog and entered the soils at the bog edge. That rain transported thermal energy because in these northern latitudes, air temperature in the spring is warmer than the soil temperatures, and so the rain is warmer than soils in the springtime. So this warmed the bog edge soils. When we have kind of early warming, we get microbial generation of plant available nutrients, and the key is that this is at the start of the growing season, and that is what allowed sedge productivity to increase and methane emissions to increase at the bog edge. And then the response at that edge was significant enough that it resulted in a 30% increase in site level methane emissions. So it was really this just kind of the edge controlling this larger site level response. So the take home message from this work is that rain is an important transporter of thermal energy in northern latitudes. But when we're thinking about biogeochemistry, it's just not the amount of rain that matters, but also then the timing of that rainfall. So northern latitudes, we are projected to get wetter and warmer. And so an outstanding question is, what role will advective heat transport by rain play in warming soils and fueling biogeochemical processes in the future? And this is a question that Joel has set out to answer with his PhD thesis, and he will present some of his work thus far trying to answer this question.
Should we wait with questions for the end of the presentation, so we can ask now?
Yeah, let's let, yeah, thanks Becca for the great presentation. Yeah, let's let Joel dive into his presentation, Vladimir, and then we'll field questions at the end.
Hopefully we'll still have time.
Awesome, is everybody able to hear me?
Yes, we can hear you.
Perfect.
And I'm just letting everyone know, if you have a question and you don't want to forget it, you can type it in the chat.
Perfect. So to begin answering this question of what role advective heat transport by rain might have in the future, as most major models are projecting northern high latitudes to get warmer and wetter, we began monitoring a site with a climate that's already warmer and already wetter in Kenai Wildlife Refuge, 450 kilometers south from the site you were just hearing about. The site's quite small. It's only about 100 meters across. In the middle of the site, we have a bog that's about 50 meters across, surrounded by permafrost underlain black spruce forest. And then outside of that forest, we have fen. This site was first established by Ben Jones et al. And in 2015, Ben's team did a permafrost survey across the site. So one of the first things we naturally wanted to do is to mimic and redo that survey when we began working at the site in 2019. This permafrost survey is a transect from this upper right corner down to the lower left, 100 meters across the site. We had one location every meter. At each location, we did 3 data points. So after 300 probes, it led to a very tired looking me and also these data. So first, looking at our y-axis, we have our 2015 depth of permafrost subtracted from 2019 depth of permafrost subtracted from Ben's 2015 depth of permafrost. All data below this 0 line indicates thaw. So what your eye is likely naturally going to are these big orange bars. These orange bars represent measurement locations that were within our measurement capacity in 2015. Both studies used a 2.1 meter long frost probe. Permafrost depth was within that 2.1 meters in 2015, but once we got to it in 2019, that permafrost depth was beyond our ability to measure. These data coincide with a 26% reduction in measurable permafrost plateau. That represents the bog expanding into that permafrost plateau, as well as the fen encroaching on the outside. And then of data that was both measurable in 2015 and 2019, we observed a 0.23 meter thaw across those 4 years, which coincides with about 6 centimeters of thaw per year, which confirmed that this site is thawing very rapidly. Our next natural question, coming off of the data that Becca presented, is if advective heat transfer by rain might have something to do with this progression. Seeking to answer this question, we lucked out. We had this massive rain event in the heat of the summer in late July, such that if advective heat transfer by rain has an effect on the site, we ought to be able to see it with this large rain event, and we absolutely did. First, looking at our hummock sites on our permafrost plateau, hummocks are local high points that are characterized by a high permafrost table, and none of our hummocks had saturated soils, so the water table was below that permafrost table. This is the same figure as the prior slide, and then right here we have a heat map created with temperature sensors from the surface into permafrost. And as we look at this heat map progressing from May through September, we see gradual thaw through May, through June, through most of July, and then coinciding with this rain event, we observed 50 to 60 centimeters of thaw in the time scale of a few days to a week. So in the Fairbanks site, we saw the ability of warm rain to warm bog soils. And these new data show evidence that not only can we warm soils, but advective heat transfer by rain has the ability to rapidly thaw soils as well. Not all locations were this extreme in response. In our permafrost hollows, the hollows are local low points that have a much deeper depth of permafrost and a pretty high proportion of saturated soils, depending on the part of the summer. We do not see a massive response in the same way we do with the hummocks with that large rain event. But if we focus in a little bit closer at these local areas of faster thaw, all of these areas coincide with rain events throughout the summer. So though we don't have a big drastic thaw event like we do in the hummocks, there is still potentially some evidence that could indicate advective heat transfer by rain may have a role. So now switching gears a little bit, going from our permafrost underlain forest into the bog itself, we also see significant signals from rain events throughout the summer. Once again, looking at our large rain event, we see that large rain event really being mirrored by a temperature signal in the bog. At the Fairbanks site, we saw temperature signals down to about 0.8 meters up to 1 meter. At this Kenai site, we saw clear temperature signals down to our deepest temperature sensor at 2.1 meters. So these temperature signals are really making their way to very deep depths. And beyond that single very large rain event, we see with rain events throughout the entirety of this warm season that we see pretty clear temperature signals throughout. One main difference between the Fairbanks site that Becca was presenting about and this Kenai site is how the bog responds after a rain event. So at the Fairbanks site that Becca presented, we would have a warm rain event. The bog soils would rapidly warm, and then the bog soils would stay much warmer. It would really be a regime change throughout that summer. We don't see that at the Kenai site. At all rain events throughout, we see a rapid warming followed by a rapid cooling. The main reason for that, we believe, is just the sheer volume of water that exists at Kenai. At the Fairbanks site, the bog is about 1 to 1.5 meters deep. At the Kenai site, this bog is much more established and it's 6 to 8 meters deep. So we just have a much, much larger reservoir of water, such that though we see very clear local warming at all of our bog sites in Kenai, the reservoir is so large that the energy input from rain isn't large enough to warm that entire basin. We just have a small period of warming followed by the basin responding and going back to a cooler equilibrium temperature. So now zoning in a bit on this large rain event to try and figure out how water is moving through this bog. We have our rain events and air temperature up above. In the middle, we have temperature sensors from the bog edge. The lighter the color, the closer to the surface. The darker the color, the deeper the temperature sensor. We have right here temperature at the bog edge, and then at the bottom at the bog center. We see some pretty clear differences between temperature at the bog edge and the bog center. Probably the most obvious is this deepest temperature sensor at 210 centimeters at the bog edge. Doesn't really experience much warming. While at the bog center, we see clear warming at that deepest depth. Additionally, at the bog edge, we see more significant warming at those shallower depths than we do at the bog center. And then at the bog edge, we see incremental warming when a rain event happens. So we see 5 to 10 degrees of increased temperature at those bog edge temperature sensors. Well, at the bog center, we really see a collapse of those temperatures, all meeting at the same temperature. So here's how we conceptualized and kind of explained those differences. So we have a precipitation event. That water is going to move through the active layer in that watershed. We expect that water to plunge, much like it does at Fairbanks. And then a difference from the Fairbanks site is because we have a smaller area in the bog, and we just have so much water that as that water comes in and meets in the middle, due to both conservation of mass and also because those rainwaters are warmer than the cooler bog water, we expect an upwelling to take place once all of that water from that permafrost circle meet in the middle. And this explains these data as we see this flow line skipping those deepest temperature sensors, which would explain why we don't see much of a response. And then because we have less overall water volume coming from the edge of the bog, we think that's why we have these more incremental increases instead of that large collapse. Well, at the center, because we're experiencing a much higher volume of water, and because we have the same water being experienced by these bottom temperature sensors, as well as temperature sensors closer to the surface, we think that is why we have these large collapses throughout that entire profile. Mostly for fun, but also as a quick check of understanding, I did the roughest tabletop quarantine physical model. This is a Tupperware bowl full of cold water, and I input some dyed water on the edges to represent rain. And we see that modeled rainwater plunging down, meeting in the middle and pluming up. before dispersing throughout that much larger volume as we would expect. So our takeaways from this section of the study is in a currently warm and wet climate, advective heat transfer by rain can both warm and thaw soils. In the Fairbanks site, we saw the ability of rain to warm bog soils and induce methane emissions. At the Kenai site, we both see the ability to warm those bog soils and also rapidly thaw frozen soils. From the repeat permafrost survey, we know that permafrost is thawing rapidly at this site, and kind of combining those results, we think that rain could be a driving mechanism. Results from both of these sites demonstrate the ability of warm rain to advect heat into permafrost landscape soils, affecting both the biogeochemistry and the thaw. But most major models do not incorporate advective heat transport. They just incorporate conductive heat transport. So due to these demonstrated effects of advective heat transport by rain, and due to the potential for this mechanism to increase in importance as northern high latitudes get warmer and wetter, I guess our general recommendation is that advective heat transferred by rain as a mechanism ought to be taken into account more widely, both in models, modeling studies, and field studies. And with that, we would love to begin discussion and answer any questions you all might have.
Excellent. Yeah, thank you, Joel, and thanks, Becca. Okay, open it up for questions now. We have about 15 minutes left on the call.
Well, can I start?
Yeah,
I have
go ahead, Bud.
probably much more questions than we can manage here. Well,
all right, I'll cut you off after about 5
yeah.
minutes.
Well, let's start with the simple one. And the last statement was that the rain was a driving mechanism of degradation of permafrost now. Well, my question is, there is any change in precipitation during the latest year compared to, say, 10 years ago?
Yeah, that's an excellent question.
So first, real quick, I don't think we're saying that it is. Our results don't let us say that rain is thawing permafrost. So
Well, that's the statement. What was the last statement in the presentation?
He
Well,
said
we saw
it could be a mechanism, and that's something that we're moving forward with testing. But I think we are very careful.
All right.
Yeah.
Answer is be careful is what you're saying, right? Because if the regime of rain is not changing drastically, probably still warming temperature, air temperature, is the major driving force of degradation of permafrost, right? Okay, well, now the more serious question, and probably this one will be only my question, but I have much more. Now, you're saying that, and that's very interesting idea, that this water coming from the plateau into the bog. Now, it's coming through the active layer in the permafrost area, right?
Yeah.
So what do you think will be the temperature of this water?
Right. So
not temperature at the arriving to the ground surface, but temperature of water already moving through the shallow active layer in the permafrost area.
Correct. So if I can share my screen.
Yeah.
We actually had, see right here. Okay, so we had temperature sensors up in that forested plateau. And so this is just showing the relationship between the estimated temperature of rain and then the soil temperature in that permafrost forest that was measured during that rain event.
At what depth?
This is that shallow depth.
And water moving through this particular depth, not deeper.
I'm sure water is moving through all of the active profile, all of the active layer. But this was unfortunately during these 3 years of the study, this was the only temperature sensor we had up in the forest. But
is it that ITEX site, or I don't remember exactly the name of it?
This is
Bonanza Creek.
But yeah, in Bonanza Creek.
Well, it should be data from the forest there. I remember there were some
Yeah, we have a flux tower up in the forest, and we had a temperature sensor there, but it was just we just had it in a shallower depth because the people were focused on the, an energy budget.
Yeah. But no, you definitely can find data from near to the place where near the bog. It's a PolarTREC site or different?
Yes. Mm-hmm.
Okay, so there definitely should be the temperature sensors and the loggers right on the edge of the forest, but in the forest on permafrost. I remember how it was installed. Actually, Bill Cable was setting this. Ronnie probably should know this.
Yeah.
Ronnie Dunham.
Yeah,
I mean,
I'm here. Yeah,
Well, anyway, it's a very important question, and you should look at it because the temperature.
So we've re-instrumented, and we have now thermal sensors throughout the entire watershed at multiple different depths, including into permafrost. So we fully instrumented the forest. It's just in 2014, 2015, 2016 when this first study was done. This is what I know to be available in terms of temperature in the forest, and this is after talking with Merritt and Eugenie and Mark and all those different people working at the site. So I'm not trying to hold anything back.
Yeah, it should be somewhere, but at least we have some site in different conditions, but in the same area.
Okay.
And another, just it's not a question, it's just a suggestion. Try to measure the flux of this water. And it will be direct evidence. So far, it's just hypothesis. That's it. Thank you.
Thank you.
I think it's a little bit more than a hypothesis, but.
Well, you have to really measure it, not because well, there's no other questions. We can continue, right? I can give you several other explanations of this data.
I'll come back to one of the initial questions that Vladimir asked, and yeah, I'll direct it to you, Joel. So in terms of the year's worth of data that you have for the site on the Kenai, how does that compare to, say, like the previous couple of decades in terms of precipitation regimes? Like, do you see a change in summer precip over time?
Yeah, so it wasn't really a super out of the ordinary year. I think having that large late July rain event isn't necessarily the most common. But we're really excited to have, it's year one of a 3-year study, both with our new instrumentation outside of Fairbanks at the Kenai site. So we're excited to have, with our rain gauge and with our temperature sensors, because there are no really high quality data that's close enough that it wouldn't be affected by atmospheric rivers and other heterogeneity in weather, that we're able to have those concrete 3 solid years of meteorological data to connect with the temperature data, such that hopefully we'll be able to, like the data that Becca presented, kind of make those more concrete comparisons hyper-local to the site and see how things are changing.
Okay, cool, thank you.
Yeah, thank you.
Anybody else have questions for Joel or Rebecca?
This is Elchin. It's more like a comment. It's not a question, but to me, it looks like those soils are quite saturated, and they already have water in the ground. So when precipitates, then it adds to that water, and then it just triggers the movement of that water. So that's not necessarily the water that comes so much from rain, but the water that's already in the soil mixed up with the rainwater and then moving down the slope, and then that sort of triggers some advective heat transport. That's why, I mean, maybe like phrasing it precipitation, it's kind of, because when we think about precipitation, we think about, oh, this is infiltration, and due to infiltration, there is some heat transport, which might not, the amount of that heat transport might not be enough because in this case, it looks more like the water moving in the ground, so it's more like groundwater movement in opposed to, it's triggered by the precipitation, there's no question about it. So there is this, there's this sort of a border, where exactly we're at. We're in groundwater sort of domain, or we're more in precipitation. They somehow, they clearly connected, but the connection there has to be, as explained, maybe a little bit more details and make some clarifications. And then, if I remember correctly, there is a paper by Ilva, I forget her second name, when she did some study, modeling study, when she showed the effect of lateral flow and the heating on, when, due to groundwater movement. So maybe it's worthwhile checking out those works as well. But other than that, it's a great work. Thanks so much.
Yeah, thank you for that. I think that's a good point. I am shared my screen here. This is a little bit more detail than I was able to go into in the short format of the talk. But yeah, so that I think you're absolutely correct in that it has to do with the watershed soils, and so this top panel is showing the cumulative precipitation minus evapotranspiration for that forested watershed. And what we were finding is not as dramatic of a response when we were getting, rain events that are occurring earlier in the season, because basically we think that that water is just kind of remaining within the forest and not making its way traveling down into the bog. And it's only, after the kind of ET demands of the forest have been met that we start to see these kind of temperature responses associated with these rainfalls. And so we are thinking of it as, groundwater flowing through these permafrost plateaus into the bog. But I think your point is well taken in that it could be more about, what the temperature of the water is sitting in the soils, which matters. That has been sitting there, say, for like a week or something before this rain event came and kind of pushed everything through. So
one more thing. Think about thermal conductivity of the upper layer. That could also explain very fast penetration of the signal. See, it's exactly, you can see very well on this graph. Yeah. On the top layer, after some period of time, it's getting dry, and that's what shows your upper graph, P minus ET. So it could get dry before rain event, and conductivity of this material, it's very porous material, may significantly lower, and then after rain event, it's refilled and conductivity may jump like 10 times. So that's another potential cause of the fast penetration of the warming signal, because conductivity of the upper layer may increase by order of magnitude.
Okay. Yeah, so I appreciate that. Thank you. I did spend a lot of time thinking about, could this be changes in the thermal conductivity within the bog soils? And our bog is like this floating mat. And so across the 3 different years, even though we had, different amounts of rain, the depth of unsaturated peat didn't change from year to year because the bog just kind of floats up and down. So that kind of allowed us to say that it wasn't, all this methane response wasn't due to like the bog soils being more saturated or, the thermal conductivity of the bog soils changing. But what you're saying, I think, is that we should be thinking about the forest soils themselves.
Right.
And those are the ones that are
especially in that hammock, situation. Hammock situation is definitely the case.
Mm-hmm. Awesome. So quickly, I think we have 1 minute. Casey Beal asked if we have any water isotope samples to differentiate sources of water. We have some pore water samples. We did not collect rainwater samples to do isotopic analysis. I did a pretty big literary review about isotopic signatures at both sites, and kind of what I got from that literary review was that the isotopic signatures from rain and permafrost, both in Fairbanks and down on Kenai, are probably too close to be able to differentiate between the two. We could differentiate between snow, possibly, but sadly the rain and permafrost were a bit too close, which is kind of what we were really, really looking for.
Oh, great, thanks for answering that. Have you also considered just antecedent conditions as well?
You mean when the snow melts?
Yeah, like timing of snow melt, even temperature leading up to rainfall, any prior precipitation leading up to the rainfall event that causes the signatures you're seeing?
I guess I didn't spend a lot of time digging into kind of those aspects of it, but yeah, it could be an important piece. Yeah, I guess for us is like what, you know, how science goes is like, I was like, oh, we're seeing this rain response. And so for a long time, I was thinking it was rain falling directly on the bog. But then you puzzle over the data and it just doesn't fit with that conceptualization. And then like the edge center differences and things like that. And so then finally, when my brain started, you know, thinking of the bog being within this larger, you know, permafrost watershed, the pieces started to fit together. And so, yeah, I don't know, it took a lot of iterations just to get to this point with the data, I felt like, to understand, you know, that what was happening in the forest is having an effect on the bog. But yeah, so part of what Joel is doing is, you know, we're really trying to expand upon this. And like I said, we have instrumented both this Apex site and the Kenai site. And yeah, so I appreciate all of these comments. They're going to be really helpful for us
Absolutely.
as we move forward.
Okay, well, yeah, thank you, Becca, and thank you, Joel, for the excellent presentations and sparking a pretty lively discussion. It's really neat work. So we are pretty much at the bottom of our hour for April. Meredith, do you want to anything you have to say to wrap up today's call, or maybe Miriam, should we provide a little teaser for the May PCT call?
Yeah, so thanks, Joel and Becca. Those were really interesting presentations. Yeah, so for May, we were thinking that it might be a good idea to have a call just on the IR 5-year plan. So feel free to attend if you have any inputs or insights you'd like included in that, the next 5 years for the permafrost team through IARPC. And also, if you have any comments in the meantime, please feel free to share them.
Yep. And I am adding to the chat here the link for the next meeting, just in case. The date might change, sometimes they do, but right now it's scheduled for May 12th. Okay, and thanks everyone. The recording will be posted in a couple of days, so that will be there. And yeah, thank you.
Yeah, thanks everybody.
Thank you. It was a great opportunity. I appreciate it.
Yeah, thanks for taking the time.